Okay, good morning everyone. Well, it's a pleasure for me to introduce you our speaker today, which is Professor Lefevre, which is going to present the IA colloquium. Olivier, well, many of you know him. He has quite expertise in, I would say, many things, but I would say surveys, extragalactic astronomy in general, and it's one of the most well-known European astronomers. He did his PhD in Toulouse Observatoire on photometry of distant cluster of galaxies, and then he was a staff astronomer of the Canada, France, Hawaii for 8 years. And the dog, yes. Then he moved back in France, and he's known because he was the who built actually the VMOS spectrograph that many of us we have used at the VLT, and still is ongoing and it's working, producing science for many years. We hope more. And that was in 2002, and this is already one of the most productive instruments at the VLT. Then he was the director of the Laboratoire d'Astrophysique de Marseille, the LAM, for 8 years, and he's still there in Marseille, and is a recipient of the advanced grant of the European Research Council. Today, he will speak for us with about the good sample. So, Olivier, please you now.
Thank you very much for your invitation. It's really a pleasure to be here, and I want to thank Carol and Pepe for inviting me here. I've been several times in Granada as a tourist, and also as in the Institute before, and so it's a pleasure to be back. So what I want to do today is to take you through the main results of the VMOS Ultra Deep Survey, which is the last of a series of surveys that we conducted with the VMOS instrument on the VLT. And I want to take an observational perspective on the assembly of massive star-forming galaxies in the redshift range 2 to 6 and some, which is where we have a strong rise in the star formation rate density in the universe. So it's really an important epoch in the formation and evolution of galaxies. And rather than to give you some scenario which would be obsolete in a few days, I prefer to give you solid observational facts that are actually a reference that models need to explain. So that's the perspective I'm going to take. So as nowadays, large surveys is always the contribution, the result of a contribution from many people, and so I want to acknowledge them. About 30 to 40 people that have been working or are still working on this survey today. Okay, so this is my outline. So just to recall the context of galaxy formation and evolution, motivate why we need spectroscopic surveys at redshift beyond 2, describing the sample of this survey, and then I will go through the properties of these faint galaxies in the redshift range 2 to 6. We'll go through describing the properties of diverse galaxy populations, looking at broad properties, the evolution in stellar mass, star formation rate, age, size, and see how this changes with redshift. I will briefly discuss environment effects on galaxy evolution, and then I will give you a few words on how we are tackling the end of reionization period at around redshift 6. And then I will attempt, some kind of a scenario empirical rather than based on simulations. And I will leave with a few words on the future prospects with the next generation facilities. So we are on this topic of galaxy evolution, galaxy formation and evolution, and these are the big questions that you can see in every book making prospective, for the next years. So what we want to understand is the origin of the Hubble sequence, galaxies that we know today, spirals, ellipticals, how did they actually form, their morphologies, when did the stars form in those galaxies, how galaxies assemble their mass. All right, so these are pretty fundamental questions, and to answer these questions, we want to identify what are the main physical processes that are at play, and when some specific process is playing more of a role than other processes. So the time evolution of these physical contributions. So it's known today that when you look back in time, galaxies have different morphologies. So this is some form of the what we call the Hubble sequence, describing how galaxies distribute in between ellipticals, various ellipticals, S0 galaxies, and then the two branches with spirals and barred spirals. And so this is what we see today, very well documented nomenclature of galaxies of different shapes. And when we go back in time, at the highest redshifts, well, galaxies don't have the same balance between types. We find more irregular galaxies at the higher redshifts and less of the organized spirals and ellipticals. All right, so there is a hint just for that observation that there is some evolution process that goes from some kind of disorganized morphologies at high redshift towards something that is well organized today. Okay, so what is the origin of this sequence that we observe today and this evolution along time? This is, galaxy evolution is of course in the context of cosmology, because we are in this paradigm today. That's our representation of the universe with the Big Bang, the subsequent evolution, expansion of the universe, accelerated expansion recently, and so it was all coded very early on. When you read the maps of the cosmic microwave background, the fluctuations in temperature that are observed, in fact, encode a lot of the subsequent evolution in large-scale structures, and actually, in the final galaxies and clusters of galaxies that we see. Right? So the seeds are planted very early on to lead to galaxies that we see today. Right? So the underlying dark matter component, which is the 23% of the content of the universe, is actually the underlying component on which galaxies are formed, right? And so we don't want to forget this coupling between the dark matter and the luminous matter, which is only, and the baryonic matter, which is only less than 5% of the content of the universe. Then there is this dark energy component, which I don't dwell into today, which is a big mystery, as you know. But this is giving us this expansion and accelerated expansion of the universe. So that's the context. And I'm placing my talk somewhere after the Dark Ages. The universe was neutral at some point, and then it got re-ionized with the first stars and the first galaxies, which cleared the neutral material so that photons could flow freely. And that's the reionization epoch, and I'm placing this talk between the end of the reionization and about a period that is 10 billion years back in the universe, when the peak of star formation was at maximum. Right, so that's the period we are looking at today. Okay, so there are a number of things that are already known, with two complementary perspectives. The first one is star formation and trying to understand what fuels star formation. Okay? There is one very famous diagram, that's the Maddow-Lilly diagram, and you can have various versions on the literature. So that's the star formation rate density, so the number of stars per megaparsec cube per year, as a function of redshift. And it's now well documented that there is a peak at about redshift 2 to 3, where from this peak to today there is a decrease in the star formation rate density by a factor 10. So it's very significant, large difference. And it seems to be, but it's less well documented, it seems to be also that beyond this peak, going towards the first stars and galaxies, so towards the reionization, redshift 6, it seems that there is also a decline, a fairly strong decline in the star formation rate density. So, what are the processes that are driving this evolution? So you are transforming gas to stars, so basic process that follows the evolution of galaxies. But you have also processes that regulate star formation, that might stop star formation at some stage. Right? So it's the competition between the processes that form stars and the processes that stop star formation that actually shape this relationship. So that's the first perspective. It's looking at star formation. There is another perspective on galaxy evolution, on how galaxies assemble, is looking at the mass buildup, and so the mass of stars, the mass in gas, and the mass in dark matter. Right? And so that you want to follow the evolution of this mass buildup in galaxies. And the equivalent of the star formation rate density is the stellar mass density. So that's what you have here. It's the number of stars that are within formed stars that are within a given volume, as a function either of redshift. I'm sorry, it's inverted. So we are here, and this is redshift 4, and this is the edge of the universe. So the Big Bang here, and we are here after 13.8 billion years. And so what is seen from various studies, one of the best ones is from Lefevre in 2013, is that there is a strong rise in the mass built up between redshift of 4 and a redshift of 1. And if you look in particular to what we call the quiescent galaxies, the ones that have low star formation, there are almost 2 decks in the mass density between redshift 3, 4 and redshift 1. So it's an epoch where we have a strong mass buildup of galaxies, and then the mass buildup from redshift 1 to now is more moderate. Yeah? There's still some mass buildup, but you see we're talking about a few tenths of % rather than 2 decks. Right? And so the quiescent population is in red here, and the black is the total population of galaxies, which shows also a similar behavior. What produces this evolution of the star formation density? What produces this evolution of the mass assembly? That's what we want to ask for. Okay, so that's another version, looking more at the theoretical perspective. We are under this hierarchical picture of assembly, where in the early universe we have small dark matter halos, and a long time those dark matter halos, you follow one branch of that tree, and this little branch here is going to merge with that bigger branch at that point, and then you have another merger with another halo at another point, and then in the end you get a big dark matter halo today. Yeah, so that's the hierarchical picture which underlines the way structures evolve in the universe. Okay, so galaxies that are embedded into these dark matter halos, as shown in this simulation here. You don't see the redshift, but here it's redshift 3, 2, 1, and 0, if I read properly. You see the little points, the little dots. The colored dots are galaxies, and the gray shade is the dark matter distribution. And so the galaxies basically paint the dark matter distribution, and as you evolve in time, you have the reddest, oldest galaxies, which are at the regions of the highest density, the highest dark matter density regions. And so that's the picture we are working with, and we are trying to prove or disprove whether this picture works as simulated in computers, right? And one of the big questions is actually that is actually with us since a bit less than 10 years, is what is the main driver for this mass assembly? Is it accretion along the filaments of the cosmic web? You see this cosmic web of dark matter. So people are claiming that there is a lot of matter accretion along these filaments falling into the galaxy that is here, and so it feeds the galaxy with a lot of gas, and of course stars will form from this gas at later stages. So that's one way to build up matter with time. As you accrete more gas, you will build more stars, and your galaxy will grow its total mass. Or is it merging? Merging is a very well-known process. We see many examples where you have galaxies close to each other in a pair, and then examples of galaxies in the process of merging. So when you take two galaxies of equal mass and you merge them, the resulting galaxy will be twice as massive. And so you build up along these branches of the hierarchical build-up. You build up mass in galaxies. Okay. And so which of these processes is dominant? Is it accretion or merging? Of course, you can well imagine that it can be both. And so we want to know when one preferentially happens compared to the other. Okay, so this is the framework we are working with. Then if you want to test these pictures with observations, it becomes suddenly much more difficult because we are dealing with objects that are very remote, very faint, and we want to make sure that we observe samples that are representative of the whole. Yeah? So we don't want to focus onto one example of a galaxy and infer the whole universe from that one example. It was something that was done maybe 30 years ago, but you don't want this perspective anymore. You want to make sure that you have samples that are representative of the galaxy population that you are measuring. So that's why we've seen a flourishment of surveys, and in particular spectroscopic surveys. This is a plot which summarizes a bit what has been done so far. So you have here the number of spectra, number of objects per square degree, and the area that has been surveyed, right? And so you see, the Sloan Digital Sky Survey in its various renderings. You have the red galaxies here. You see, all the early surveys like the CFA surveys. So that's the surveys that are in the local universe have a low density of objects, but they survey large areas, all sky. And then when you go to faint surveys, faint galaxies going to higher redshifts, that's where you have a number of surveys like the Deep2 on the Keck, like the VVDS, Z-Cosmos, and Vipers on the VLT. You are getting high density of spectra, but on small areas. That's always a difficulty in surveys to survey large enough volumes with large enough numbers of galaxies, and it's been the whole game with instrumentation to try to populate both faint and in both very faint, very distant galaxies, but also in large volumes. And that has proven to be difficult. Okay, another point that is quite sobering when you look at the literature is that there is a lot of studies beyond redshift 3 which are in the literature, and when you look at the samples, most of what you see is based on photometric samples. Right? So the photometric samples, we use photometric techniques to have an estimate of the redshift. So there are a number of ways to do that. The one well known is to look Lyman break selection, where the IGM between us and the distant galaxy is producing a break in the continuum of the object, and so using broadband you can identify distant galaxies. Another a bit more sophisticated technique is photometric redshifts. So you use multi-band photometric information and you do some kind of galaxy template fitting that gives you also an indication on the redshift of the galaxy. So that works relatively well, except that as an observer I still don't know precisely where it stands in 3D in space. And so for that you need spectroscopic redshift information, where you are able to place in a map, on the 3D map, where that galaxy stands, and with respect to its neighbor, and have an accuracy of measurement of the spectroscopy of the redshift that gives you, that makes you secure in putting a point in the evolution of the star formation rate density. When you measure a sample, you want to be sure that it's actually at redshift 4 and not at redshift 2. Okay, so you need spectroscopy. All right, so that's one thing that is missing at redshift beyond 2, 3 is large samples of objects with spectroscopy. Another thing that is missing is the sampling of large volumes. Most of what we see again is based on small fields. Take the HST surveys. HST has a small field of view, and so you get surveys that are a few tenths, a few hundreds of square arc minutes. Okay, and you're deriving your knowledge of the whole universe based on 500 square arc minutes of observations. And so we know that there is cosmic variance. There is a nice paper from Moster in 2011 that explains all of that. And so if you take arc minute scales like the Muse spectrograph on the VLTs, 1 by 1 square arc minute, the cosmic variance on the 1 square arc minute is a factor 3. So if I take 2 fields separated, each 1 square arc minute, I can find a difference in the number of galaxies of a factor 3. It's huge. Yeah? If I go to 100 square arc minutes, surveys like GOODS or CANDLES, the variance is 50%. It's still large compared to measuring an average average properties with good enough accuracy. And even on 1 square degree, which is the size of the cosmos field, the HST cosmos field, it's still about 10%. Right? So that tells you that if you want to conduct surveys with enough accuracy, you need large samples of spectroscopic redshifts on large fields. Okay, and then the game becomes a bit complicated. Okay, so just to illustrate why it's becoming complicated, and not why it's becoming complicated, but it's complicated because the fact that it's complicated leads to this distribution of number of galaxies as a function of redshift observed in spectroscopy. All right, so you see a number of samples here. So there are the big one here is the Z Cosmos Deep, which peaks at about redshift of 2. You have all the work from Steidel and collaborators, at about 2,000 objects that is here, peak at redshift 3. And then you have a number of other spectroscopic samples that are identified here. So you see that it reaches very high in redshift, redshift 7 and now more. I mean, the largest redshift identified is beyond redshift 8. But it tells you that beyond redshift 3, there is kind of a desert. It's not because it's a desert in the universe, of course. It's just because it's difficult to observe in spectroscopy in this redshift range and acquire a large number of objects. So that's what we said to do with the VUGS, is to actually define a survey where we observe 1 square degree, so in 3 fields, and so that to mitigate this cosmic variance that I was speaking about, reaching about the 10,000 galaxies observed for number statistics. We selected by photometric redshifts, but being careful to select with the first and second peak of the PDF. And I have no time to explain to you why I said that photometric redshift was no good and why we are selecting in photometric redshift. We can discuss afterwards, but that we did it in a way to be all-inclusive rather than to be exclusive. With photometric redshift that work quite well. There is a cloud here that we took care to target. You see that there are high spectroscopic redshift, but in photometric redshift they are at low redshift, and that represents about 10% of the population, which was important to get in. Okay. All right. So we did it in those 3 fields, total of 1 square degree. And you see the paving with VMOS is a bit complicated in geometry, but okay, that's what we are dealing with. Being in Cosmos, ECDFS, and the VVDS 2-hour field, we have a lot of ancillary information from all the photometric bands you can imagine, all the way to Spitzer and Herschel radio, and so that's these are great fields to work because we can combine a lot of information with the spectroscopy. So this is my baby VMOS on the VLT Nasmith Focus, so 8-meter telescope. It has a field of view of 220 square arc minutes. And in one shot, it can take about 600 objects that are observed through slits. You see one of the 4 masks here. You see the slits that are cut in this metal sheet. It's about 40 centimeters, so it's on the focal plane. It's a pretty big input to the spectrograph. So we do observe for about 14 hours in a blue setup and a red setup of the gratings, which gives us about an 80% success rate down to magnitude 25. Those of you that observe galaxies know that getting to 25 at 80% success rate is difficult. And so, that's what we succeeded to do, and that was really hard work. And you see that it's hard because we not only want to detect objects with emission. So of course, when you have emission line, it's easier to identify the redshift for one, but also galaxies with only absorption. Okay, you see 2 examples here, redshift 4.4, 4.6, yeah, where we are very well able to detect both the Lyman limit, the Lyman break at Lyman alpha, and other absorption features. Yeah? So that turned out to be very nice. I'm not commenting on this. So that's the redshift distribution of our sample. So we selected beyond redshift 2, so that's mostly what we get. Okay, redshift 2 and above, up to redshift 6.5. But also we have a lower redshift sample, which is the result of 2 things. First, we included a purely magnitude limited sample at 25, so no color selection, no photometric redshift selection, and also it's populated by the photometric redshift failures that were input into our selection, and so we have a good control of the selection in the end. Once you have the spectrum, you can do many things, and one thing that one of my ex-students, Romain Thomas, did is to develop a way to do spectral energy distribution fitting, where you compare your data points to reference galaxy templates from stellar population composites, where you combine the spectroscopy, that's in black, with the photometry. Unfortunately, you don't see very much. Well, you see it on this one here. You see the green points are the photometric points, and the black line is the observed spectrum. And so when you do SED fitting, combining the spectrum and the photometric points, you are able to improve the measurements of a number of things like the stellar mass, the star formation rate, the age, so physical parameters on your galaxies. So this was before we came, and this is after. All right, so this is what we brought in, this gray distribution of galaxies from the VUD sample. So at all redshift, we multiply by factor 2 or 3 the total number of spectra that were available before. So this is in one shot, putting 7,000 spectra together from redshift 2 to redshift 6. So we build this picture in putting one spectrum per line, and putting the spectrum, ordering the spectra per redshift. And this is very nice because you can follow all the features that you can observe in rest frame ultraviolet. Even though it's observed optical, but it's probing rest frame ultraviolet. So you see the most prominent is the Lyman alpha line, which can be in emission or in absorption, and we follow it all the way to the whole redshift range. You can see the Lyman limit that is here, and then you can see all the you can see carbon 3 in emission here, right? And you can see a number of other features, carbon 4 in absorption, and all the absorption features that we can work with. So that's the data that we are getting. So of course the signal to noise is not very high in galaxies, but there are a lot of things that we can do besides having the redshift. And these are summarized here. I'm going to go through some of that, so you can look at the different galaxy populations, you can look at statistical functions, and you can look at distributions in large-scale structures because of the relatively large volume that we have been working with. Okay, so what I want to convince you is that there is a large variety of galaxy populations Okay, so we are targeting by selecting with some high band selection. We are targeting star-forming galaxies. It's not an infrared selected sample. So we are targeting star-forming galaxies with little dust obscuration, but within this sample there is a large variety of objects. In terms of age, in terms of sizes, in terms of the line emission, in terms of the types of progenitors you can observe for different categories of galaxies. So let me go through some of that. The first is one key question that has been with us for a long time is what is the epoch of galaxy formation? It's a very simple question, but so far, there are not many answers to that. The way we have been looking at it is to say, well, let's perform edge measurements. And so when you say that for people that work in the low redshift universe, they say, no, edges, is very difficult to measure because we have degeneracies between dust, metallicity, this and that. But it turns out that when you go to higher redshift, it becomes easier because the edge of the universe at that epoch is smaller, and so you don't have time to build a lot of metals, you don't have time to build a lot of dust, you don't have to, okay, so things are simpler, and you can converge into edge measurements that was demonstrated in simulations where degeneracies can be lifted or partially lifted, when you combine photometry, UV ray spectra, and the edge of the universe. So we have edge measurements, which are in this distribution here. This is the edge of the universe at particular redshift, and so you see that you have galaxies that span edges, from very young to as old as the universe allows at the particular redshift of observation. And so that's something that then we can turn into what we call a formation redshift function. So you look at the number of galaxies per megaparsec cube that are formed at a given epoch. So if you want, it's the equivalent of the luminosity function, but it's the edge function, formation edge function. And this is what we find, and it's a remarkably constant function as a function of the observed redshift. So we can do this with a sample between redshift 2 and 3, 3 and 4, and beyond redshift 4, and you see that the three functions are actually very similar. And so you work with formation age. And so what we see is, our galaxies, the galaxies that are observed in our samples, so star-forming galaxies at redshift 2 to 6, they have formed from redshift, about 4 to about redshift 15 with this number density. Okay, so actually the formation of galaxies is a continuous process, and you have few galaxies forming at high redshift and a lot of galaxies forming as you are coming close to the peak of star formation density. This rise here of this function is about the same as the rise in the star formation rate density. And so that's, we think, an important function in the future to try to refine so that we get the evolution of the, as we get an indication on when the first galaxies form. All right. I may not want to get into this. This is, there is a well-known trend of galaxies in the local universe, which is called downsizing, which says that when you are a massive galaxy, you have been born earlier than less massive galaxies, right? So it's called downsizing because it's opposite to the trend I've been describing of hierarchical buildup. But it's so it's anti-hierarchical, but it's well understood. I mean, there's a paper by Gabriela De Lucia in 2006 which explains all of that. So the question we ask ourselves is, when did this happen, this downsizing? Is this something that is innate, or is something that happens after some time in the universe evolution? And so, what we are doing here, we are plotting the cosmic time, the observed epoch of formation of galaxy as a function of mass, stellar mass, in different redshift ranges. And so, when you are at low redshift, at the peak of star formation in the universe, redshift 2 to about 2, we see downsizing. That is, you see that the less massive galaxies have been forming later than the more massive. But when you go by redshift 4 or so, you don't have a downsizing trend anymore. And so it means that downsizing appears, the galaxies differentiate versus mass at about a redshift 4 in the universe. So that's something interesting that we are checking with people doing simulations on whether they find the same, and they seem to be finding the same, as is shown in this plot here. It's a paper that is submitted where the blue points are from one of the Gallic simulations compared to our data points, and it seems that we go from this hierarchical to this downsizing at about redshift 4. All right, so I'm sorry because I'm jumping topics to topics, yeah, but that gives you, it's to give you a picture. Yeah. So now let's look at galaxy sizes, which you expect as galaxies are building up, that their sizes somehow will change, and maybe the sizes should increase with time. Traditionally, of course, you do galaxy sizes at this high redshift based on HST imaging because you have the spatial resolution. So we took the sample, the VUT sample, which is in Cosmos and candles, so with HST imaging, combined with our spectroscopic redshift to measure sizes and to look at size evolution. So the classical picture is that when you look at the effective radius, so it's about the half-light radius of a galaxy. The classical picture is that these sizes are decreasing with redshift. Okay, you see it's quite a dramatic trend because you shrink the sizes of galaxies, from about 2 megaparsecs in equivalent radius to below 1 kiloparsecs. Yeah, so it's quite a large reduction in size. So this was before us. There are a lot of technical reasons to think that this is flawed. And one of the main reasons is that when you compute the radius of a galaxy, when you do it on a galaxy with a regular shape, it's easy, right? I mean, you can fit a profile, you can measure radius at various depth in the profile. But when your galaxy is irregular, you have a trouble because you cannot project a symmetric model onto a galaxy which is asymmetric, right? And so measuring effective radii onto the high redshift galaxies which are irregular, we are proving in this paper that this is not the right way to do. And so if you instead of working on an effective radius, you work on a total radius, which is related to the depth of your images. So you have to be careful taking care of surface brightness and surface brightness dimming and so on. Well, here we find that the sizes of galaxies, the total size of galaxies remains rather constant with redshift, with a large scatter. Okay, at all redshift there are galaxies that are very big and there are galaxies that are very small. Okay? But on average, the total size is getting more or less constant. And it's a point. If I take my hat of looking at instrument building, you want to make sure that your instruments that you are building don't assume that you have point-light galaxies at very high redshift. You want to be sure to assume that there will be some spatial extent, and integral field spectroscopy and those kind of things. Okay? And so, the thing that is important to realize is that, the fact that we have, not only this constant total radius, but the scatter I was mentioning to you, means that, there are different assembly processes that are working. For a galaxy at redshift 4 to be super compact or to be very large, can be the same process that has formed those two galaxies. Right? So, and I'm going to comment on that next. All right, let me go through the spectral properties of the galaxies. This is, you can find that in my 2015 paper. These are stacks of galaxies, just to show you, the wealth of features that we get. So this is between redshift 3 and 4 and redshift 4 and 4.7. There's about 400 galaxies in this panel that have been stacked, 170 here and about 280 here. So all galaxies here, galaxies with Raman alpha emission here, and galaxies with no Raman alpha emission here. Right? And you see that we can get a number of features. identified some of them. Of course, below Lyman alpha, what you see here is the result of the IgM, that is, between you and the galaxy. Then you get the Lyman alpha line, and then you get a number of lines like carbon 4, helium-2 here, this little blip in emission, carbon 3, you see it in emission, it's ubiquitous. Okay, so that's what you can work with to try to have some spectral diagnostics on your population. One thing that we realized quite early that was that, as I was mentioning, carbon 3 is ubiquitous, so it's present in most galaxies. And we concentrated into the strongest carbon 3 emitters, which is an indication of a strong photoionizing field. That's work in progress where, here I'm showing you a stack of the 20 strongest emitters. So it's rare population, it's 20 among 7,000, but you see super strong emission lines, like carbon 3 is here, you see helium-2, you see oxygen-3, carbon 4, and a number of other lines. One thing that Daniel Scherer and Nakajima is doing is actually trying to find diagnostic diagrams where you can try to separate, a bit like the BPT diagrams at lower redshifts, what is the locus of active galactic nuclei versus the locus of star-forming regions. And so that's work in progress that I hope we will submit soon, where there seems to be quite a trend in looking at carbon 4 over carbon 3 and a combination of carbon 3, carbon 4 versus helium-2. You can draw some kind of a separation lines. So it's a first indication. The points that are of interest, I'm sorry, that's the gray points here are from the Wood sample. So most of them are on the star formation region side. The red points AGNs is a calibration sample to make sure that we understand the process. So it looks like that's photoionization by hot low metallicity stars, and that's a nice work in progress that will of course benefit over the years to refine the measurement of the line for each galaxy. Carbon 3 has been proposed in the literature by people working in the reionization epoch as a substitute to Lyman alpha when there is no Lyman alpha in the galaxy. They say, well, what are the other lines available? Well, carbon 3 is one. So we looked at the carbon 3 equivalent width distribution in our sample, and you don't have strong carbon 3 emitters. The typical is about 10 angstrom equivalent width, and so even though the fraction of carbon 3 emitters above 10 angstrom is 25%, it's not really a substitute to Lyman alpha at high redshift. So it's not because when you observe a galaxy at high redshift you don't get Lyman alpha or you don't get carbon 3. It's not an indication that it's not a high redshift galaxy. All right. Enrique knows very well this work because he's a co-author here. That's the identification of young forming dwarfs with low metallicity. So we are at a redshift of about 3. We found small objects. You see some images here. So pretty small condensed object, except that some are have a double structure, might be mergers. We'll come back on that. So they are subluminous compared to our galaxy. They are 10 to the 8, 10 to the 9 solar masses, and they have bright nebula lines. Okay, you see a bit like the spectrum I was showing before, and so this is an indication of low gas phase metallicity, where you can populate the metallicity mass diagram here by the red points here on the low mass end, and extend the relation that was established by others before. So it's a nice result. It's submitted to Nature. Should be accepted soon, I hope. Quick word on helium-2 emitters, because I know that it's the pet work of some people in this room. So we have not done much on the Wood sample itself. We had identified from the VVDS, which was a previous survey, 2 types of strong helium-2 emitters, either broad or narrow. And on the narrow ones, we had proposed that it might be POP3 population that has left over to a redshift 3, so leftover pristine gas from early formation. And this is really something that we are discussing here with Carol and Pepe, is to see, well, let's try to do follow-up studies at higher spectral resolution, and Megara is one of the possible ways to do it, Megara on the GTC, so that we can look at this population and really try to understand what we are dealing with. Are we really looking at very pristine populations, pristine gas that is forming first population of stars, or is it some more complex process of star formation? So I hope we can keep working on this together in the future. All right, so another population that was very surprising to us is the discovery of extremely compact galaxies. So this is a stack of those very compact galaxies, which is basically unresolved under HST images. So it's galaxies which are super small. And they are galaxies because, we see very well the Lyman alpha emission or the Lyman alpha absorption and break. And so, we have the spectroscopic redshift. And so these are very intriguing because how can you get such a high star formation density? If you look at super small galaxies, we estimate that they are at about 100 or 200 parsecs size. But they shoot a lot of star formation, and so the star formation density in this volume is very high. And that's something that we are trying to discuss with various people doing simulations of star formation, and the first blocks, proto-galaxy blocks that are forming, and try to see whether they see it in the simulations. It might be that as the universe was denser at high redshift before the expansion, it might be that when some of the first galaxies were formed, the collapse was going to be very massive in a very small volume. And that's the one thing we want to reconcile with and to try to understand this population. What is this population going to evolve into at later stages is still unclear. Are we seeing the nucleus of elliptical galaxies or not? So it might be yes in some ways, but no in some other ways. Okay, let me jump on this. Because if we do the reverse process, if we look at compact quiescent galaxies at redshift 2, which is a population that has been notified now for some years, the question is, what are their progenitors? And what we find is that the progenitors of compact quiescent galaxies, which are going to evolve into ellipticals today, when we look at them at higher redshift, they are not compact. Some of them are compact, some of them are not. And so, it calls for different processes of formation rather than compact leads to compact. Okay, compact may have been extended in the past. And so, that's the question of progenitors and descendants, which is not easy to tackle because you need to follow populations that are similar, and that's something you can do by looking at mass cuts and so on. That's work in progress by Lydia Tasca, and I hope it's going to give some interesting papers very soon. Okay, so let me maybe jump a bit further here. There is a classical now in the literature reference to what people call the main sequence of galaxies. So it's a sequence of galaxies distributing along a line where you have stronger star formation when your galaxy has a larger stellar mass. Okay, it's a bit understandable that if you have galaxies that are forming more stars, it will end up to have more mass. All right, so that's the underlying principle, and so that's this main sequence. You see many papers on the literature. What we are showing with the VUDS is that this is the ensemble of galaxies that are observed here. If you do a median average, these are the black squares. Well, you see there is a turnover at the bright mass. Okay, and we are not the only ones to find that, it seems. It might well be that this turnover is because this massive population is starting to be quenched. That's one of the processes where star formation is stopped. Okay, Okay, so you have a strongly star-forming galaxy, so a high star formation rate, and then for some reason the star formation is stopped, and so the star formation drops, but the mass is still increasing. Yeah? And so that might be one reason to explain that. So what can produce quenching? There is what is called feedback from supernova or from AGN, where you have winds. Winds can shut down star formation. Okay, so that's one of the processes that can quench the star formation. Okay. You can translate the star formation into a specific star formation rate by dividing by the mass. So it's a star formation rate dividing by mass here as a function of redshift. And so you see our color points here compared to some others in the literature. So the observations find that there is a steep rise to redshift 2, and then there is some kind of flattening beyond redshift 2. It turns out it's not compatible with the models that you see, the dashed lines and the dotted lines and so on, which are pure accretion models, which I was referring at the beginning of my talk. So if the mass buildup of galaxies is purely accretion, it doesn't fit with observation. So it must be that there are some other processes that are going on. Accretion alone cannot grow the specific star formation rate. So what can contribute to the mass growth? So it's mergers. We have done an earlier work in 2014 measuring the redshift of each galaxy in a pair to confirm with the two spectra that it's indeed a physical pair. Right? So we have the separation and the redshift, the velocity difference. So we can prove that two galaxies close in space. It's not just by chance projection along the line side, but it's really a redshift, a physical pair. So we find that about 20% of galaxies are in major mergers at redshift 3 to 4. And if you integrate this major fraction to redshift 0, a galaxy at redshift 3 will have doubled its mass by redshift 0. So it's very significant. The contribution of the mass buildup of galaxies with merging is large. Another evidence for this merging process is very nice work that is done by Bruno Ribeiro. He's a student with us. He's defending his PhD very soon. If you have a postdoc for him, look for him. He's really bright. And so he's been doing all sorts of analysis of these images. And what he finds is that you look at all galaxies at this redshift, and you count the number of clumps in each galaxy. Okay, so you have systems where you have 2 clumps. Okay, you see the 2 clumps here. The radius is 20 kiloparsecs. And then you have systems where you have multiple clumps, more than 2 clumps. Okay, you see those systems here. So you count the clumps above a given luminosity. And so the clumps in galaxies we are told by the people doing simulations, they can be the result of several processes. Of course, a massive star formation region, so for transforming in situ gas in stars, violent disk instabilities, or dynamical processes, or merging, major or minor. And so can we infer the relative contribution of each of these processes beyond the dogma of cold accretion, which is, as you can see, I have a bias against accretion, but okay, cold accretion plus violent disk instability is what you find in the literature as the way to build galaxy disk and the only process that works and so on. Well, okay, so we do basic astronomy, we count things, so this is the number, it is the fraction of galaxies as a function of the clump numbers per galaxy. So you find that most galaxies have only 1 clump, but then the second most dominant fraction of galaxies has 2 clumps, and then 3 clumps, 4 clumps, etc. Okay? So when we first did this plot, we were immediately struck, because how can a disk fragmentation based on instabilities would predominantly produce 2 clumps? I talked to people doing simulations like Frédéric Bourneau. He says it's impossible. I mean, I have no way to explain why a disk fragmenting is going to preferentially build 2 clumps. Okay, so that was the first things where we scratch our head, and then Bruno, what he did is he plotted the total area here versus the magnitude, the absolute magnitude of the clumps, and so what he finds, which is I think very clear, is that getting out of battery here. So the large clumps and bright clumps are here, And so the large and bright clumps are in 2-clump systems, while the small and faint clumps, the ones here, are in multi-clump systems, more than 3 clumps. All right, so, this part here, large and bright clumps and 2-clump galaxies are major mergers. Okay, and we can derive a fraction which is again about 20%. So it's conform to what we have measured before with spectroscopy. And the other clumps here are likely, but it's an indirect inference, violent disk instabilities. So where a disk breaking up in various pieces. And so there are the 2 main modes of galaxy assembly that we see at work in those high redshift systems, merging and some disk instabilities that would contribute together to forming disk. So I'm running out of time, so let me jump a bit ahead. So we have a number of protostructures identified. I have no time here. Just to mention that we can link galaxy properties to the dark matter halo properties using halo occupation models. This is very nice. You can look at the efficiency of the star formation. And let me just tell you about the end of reionization, where we are using the Lyman alpha fraction, the fraction of Lyman alpha emitters as a function of redshift, and trying to enter into the reionization era. We have published that in 2014. We are now assembling, it's the final work for the VUD sample, is to extract those single line emitters in our spectra, which turn out to be redshift 5.5 to 6.5. We have about 100 galaxies in this redshift range. You see one of the stacks here. You can see Lyman alpha and the Lyman limit here. And so we are actively working on this sample to try to finish it up, so that we can say whether there is a drop of Lyman alpha emission beyond redshift 6, which has been put forward as a sign of the end of reionization. So it's the last bit of work. Some of our data is public. You can get the DR1, which is on all the Candles fields, Cosmos and ECDFS, and we are publishing next release by early next year on the Cosmos field. So let me just give a word on the galaxy evolution scenario. Just put it back together. Yeah? So we have identified several key processes, right? There are direct identification of mergers, of course, stellar evolution, and maybe disk instabilities. Yeah? We have indirect evidence for accretion, for feedback, and for the effect of environment. Right? So these are the main physical processes that are at work to shape the galaxy evolution. Okay, we have quantified some of these properties over more than 12 gigayear. Okay, so this is an observational reference that exists, and that models need to be taken into account. And so now we need to look at how semi-analytical models confront with our observations, and they are semi-successful. And I would say that there are some little failures that indicate that the models are not yet up to par with the high redshift population. Okay, it's not to say that our colleagues doing simulations are doing bad work. It's just that it's very complex, and so the complexity of the models is getting higher and higher. And as you know, they are not predictive enough. They are reacting to the observations rather than predicting, and so the models are a bit, not so useful, I would say, beyond understanding, some detailed populations, which is really nice. So let's look at what people have been proposing. There was some time ago, like 10 years ago, proposal by Lefevre, with this, color, which is star formation in some ways, and stellar mass. You go from a blue cloud with merging to the red sequence. Here you have wet merging. Here you have dry merging. Okay, and you get some quenching at some mass. Okay, that picture has some interest, with the quenching that I was reporting, and the merging that we see at high redshift. So that picture applies, I would say, below redshift 2 more nicely than at high redshift. Hopkins 2008, with this whole series of events as drawn from his simulations. I'm not going through that, but it's interesting to read. You have the history of star formation, you have mergers, you have central black hole formation. So that's interesting, but it fails to do two things. It fails to build up massive galaxies, and it fails to reproduce the density of low-mass galaxies. So it's a bit difficult. So rather than to give you a scenario, I'm just summarizing here, various physical mechanisms and whether they have been observed, whether they are expected to contribute to evolution, their timescales, so that you can build up your own feeling about what's happening. Okay? So stellar evolution for sure is observed. We see the evidence of the star buildup. We see different stellar populations as a function of time, so that's clear. Merging, I think, is very clear. It's direct measurement of the merging fraction, merging rate. Disk instabilities, it's indirect evidence, but I think it's one of the few ways to explain the multi-clump systems. Accretion, although it's the main mechanism that has been called by many people to build up galaxies, there is no direct evidence except one. There is one paper by Boucher et al. Where they see infalling material onto a galaxy by using a transmission towards the line of sight of a quasar. And so, the question of accretion remains with us to prove that accretion is working on which scales, on which time scales, and I think it's a very important item to track in the next years, is to finally prove how accretion works. And models are nowadays a bit in a fight between this filament accretion I was describing, or when you look at illustrious simulations where the accretion is more smooth. So a lot of work around this item. The effect of large-scale environment, there will be a number of things that will be coming up from our team in the future. It's clear that environment has an imprint on galaxy evolution, and you see the type density relation, for instance, it's changing with redshift, and so on. We see evidence for quenching and feedback with outflows is something that is observed. So all of that is starting to be quantified, to be put together, and I think it's up to us observers to actually consolidate this picture so that finally the people doing simulations don't only look at their computers but also look at the real universe. And I'm stopping here because I'm late. Thank you.
Thank you very much. That's amazing results. So it's time for questions now.
I have a question.
Okay, go ahead.
For the galaxies from BUDS, do you think we can measure the UV continuous low, the beta parameter?
Yes.
Yes, so the continuous detection is enough.
Yes.
Yeah.
Yeah,
And
there
have
is-
you measured the value, so do you have?
Yes. There is a first paper you can look for. It's at redshift 2 to 2.5, so the lower redshift end of your sample. Look for Hattie et al. HATHI. It's published, and we are working on the higher redshift samples. And yes, we detect the continuum on most of the galaxies.
Because this parameter is very important because
Yes.
it gives information on the young stellar population. And I'm just thinking that for the helium-2 emitting galaxies, it will be good maybe to check if there is a trend between the beta value and the luminosity of the helium.
Sure, yes.
This is something interesting that we can.
Yeah, it's a good comment. Yeah.
More questions? Sorry?
In fact, I have two questions. First one is that you have said that you have 4 possible origins for studying clumps in the galaxies. So the two first will start measuring these instabilities. So the question is, how do you differentiate between the two processes? So how do you make the difference?
Yeah, good question. It's really hard because the clumps are supposed. The disk instability is supposed to evolve with time, and what some people say is that ultimately the clumps may merge and forge a central protobulge. And so there are some dynamical arguments. If we can measure the lifetime of clumps, then we could differentiate between star clusters that are formed in situ or star clusters that are formed in disk. And we are not yet there. There are first measurements, very preliminary, that say that clump life might be of the order of 100 to 500 million years. Okay, but it's not yet conclusive.
And And the second question is regarding AGN. Do you have any information? I hope, I imagine you have so. How is the rate of the AGN in your sample as compared to low redshift AGN? So how does that evolve?
Right. Okay, so quite amazingly, we have few AGN in the sense of broadline AGN, type 1. Okay. So quasars, we have a few, but not many. Where it's becoming more difficult is to identify Seyfert activity, right? It's part of the one of the diagrams I was showing, diagnostic diagrams, to try to see whether there are some objects that are more on the AGN side than on the staff arming side. So far, what we see is that it's if there is AGN contribution, it's only a small fraction, or it's hidden by dust or whatnot.
But you have X-ray information, right?
Well, but X-ray information that is available at this redshift is not deep enough to be discriminating. So, might be Athena maybe in the future.
Yeah, thanks for your talk. It was very interesting and with a lot of questions to think about. I would like to mention, yes, as a comment, and I would like to know your opinion. What will be the contribution of SKA and the radio surveys in this field? I think in many of the questions you have posed, it would be very, very relevant. I mean, I'm thinking, for example, in this population of extremely compact galaxies, in what you mentioned about the total galaxy size that remains constant with redshift, and the contribution from even the differentiation between these stabilities and other options.
Right.
Well, do you have any comment? Because there will be very deep, high resolution surveys with SKA that I think can really help a lot in this.
Yeah, thank you for the question, and I'm extending it also to ALMA.
Yeah.
Okay. Because one of the things that can be done is that I've not spoken about too much is to try to track the gas reservoir, right, as a function of time. What is the fraction of gas to star as a function of time? So specifically on SKA, I'm external to it. Actually, we are trying to prepare a joint Euclid SKA meeting to see whether things can be put together. The understanding that I have now is that beyond redshift 1, it's going to be difficult to track H1, but that's something that a few years past I was told it's going to be easier to redshift 5. Now I hear redshift 1, so I'm a bit. I want to see. It would be great if we can do it.
With the phase 1, I agree, but with the phase 2, it will be possible. But in any case, referring to continuum, on the continuum you can get a lot of information also, I think.
Yes.
Not only with phase 1. I mean,
Okay,
with the continuum, you can go up to redshift of around 4 with for stack formation rates of the order of 150 hundreds or masses per year, something like that. And you will have, I think, very good resolution that really can be very relevant.
Yeah, it's a very good point. I
Really?
fully agree. Yes. And just a small comment on ALMA, that's also one way. I mean, there are some indirect ways, like using the CO content, that you can track the gas and so on. There are also tracers like carbon-2 that are used as maybe star formation tracers. Okay, so the multi-wavelength perspective is very important.
I enjoy a lot your talk. Thank you. I have a technical question related with the determination of the epoch of the star formation,
Yes.
which is based on the ages. But I wonder how can you distinguish the affair of the degeneracy between the ages and the extinction? Because I suppose that these galaxies are not very extinguished, but there is a small extinction can affect a lot to the ultraviolet emission.
Right. Yes. Well, okay. So that was I unfortunately I went very fast on too many things. The key point is that sorry, too many plots. The main point is that we are using the UV reference spectra. The black line here is the spectrum as observed by VMOS, combined with points all the way to 4.5 micron of speed zero. Okay, And so when you do the combined set fitting of spectroscopy plus all the photometry, I'm not saying that you completely break the degeneracy, but at these redshifts, you get an estimate of the dust extinction, which is, as we've shown from simulation, which is a first good approximation. Okay, and so the UV corrected from the dust extinction then gives star formation rate and so on and so forth. Okay, so we have a first estimate of that. For sure, we need to improve on that in the future by going towards red spectroscopy in the near infrared and so on, and getting. But we have a first estimate,
So it is basically in the spectral fitting using the combination of the ultraviolet with the optical.
Yes.
Image.
Yes.
Continue.
More questions? I have a comment. I really like when you mentioned that this result by Thomas and about the new downsizing, let's say, scenario, where you have this that depends on the redshift range, the redshift window you are sampling.
Mm-hmm.
So you say that there is no downsizing measured at a given redshift.
Right.
You compare with. Can you elaborate a bit more? I mean, these are the same galaxies. I mean, for a given mass, are all these galaxies the same more or less, or what is different between this no evolution with time and the this plot?
Well, so first we took care. Okay, so the on this mass range, our sample is complete. Okay, except for those galaxies that have too much dust that we don't select because we are selecting based on the UV. Okay, so we are looking at the same population at different redshifts. The thing is that
I mean, in other properties.
There is nothing special. It's the average of the population, and so that's the result came out. We were first surprised to see it because it comes without any tuning,
sure.
and so looking at the simulation. Okay, the simulations can be useful in this type of cases. It looks like it's coming from the fact that there might be a mass limit for the star formation to kick in at some epoch, and that gives you the mass dependency that then builds up with redshift, because this mass cutoff is changing with redshift. The star formation will be triggered at different masses as a function of redshift. That's what I was explained by the Galix people doing the simulation. And so, again, when we plotted this thing, the blue points are from the simulations, and we have actually an updated plot with some errors on the simulations. It came out exactly the same, and so without no tuning and no anything. And so, it's the first time actually that I see simulations predicting something that we verified by observation. But yeah.
Great. There's no more questions. There's no more questions. Thank you again.
Thank you.